Section 1.3, Data Collection and Experimental Design. So there's multiple steps to designing a statistical study. First thing is identify the variable of interest in the population of the study. What do you want to study? Maybe it's how many push-ups can everybody do after COVID is over, after staying at home all this time? Or maybe it's what's the average hours Publix employees are currently working. So identify what and who you want to study. Step 2 is develop a detailed plan for collecting that data. If you're using a sample, make sure the sample is representative of your population. So if I wanted to do Publix employees, I probably couldn't talk to all of them. So would it be reasonable that I could get to 50 of them? How would I talk to them? How would I select which 50 would I be talking to? Things like that would be in your detailed plan. Then you go out and collect the data. Actually go talk to the people, send them the survey, do the thing, get all the information so that for number 4, you can describe the data using descriptive statistics techniques. So that's a lot of the stuff we'll be talking about this semester is how you summarize the data. What can you do with that data? So that number 5, you can interpret that data and make decisions about the population using your inferential statistics. So maybe if you only talk to 50 Publix employees, you gathered all that information, you could make conclusions and make statements like Publix employees are working currently 30 hours a week compared to a previously 20 hours a week. You can make blanket statements about everyone. And the last one, the one that often is not talked about, but it's kind of like the end of a math problem, you always have to go back and check your work. So number 6 is identify possible errors that might have occurred. Maybe you wanted to get 50, but you only ended up getting 30. It was harder to reach them by the phone instead of going to see them in person. Or maybe you tried to do a random sample of everyone, but you ended up getting all boys. You didn't get any females in the group. So that would be a chance for you to kind of go back, make note of any issues so that if somebody goes and does this again, they can improve on it next time around. Now, under the data collection, one of the ways you can collect data is by observational study. So that's when a researcher observes and measures characteristics of interest of part of the population. So an example for that one here says researchers measured the amount of time people spent doing various activities such as paid work, childcare, and socializing. With observational, I always think of psychologists because especially with a child psychologist, you can't always just ask them information. You have to watch them and see how they interact or how they process things. So observational, I always have this image in my mind of somebody watching somebody else, just not interacting, just kind of collecting the information, especially with toddlers. Are they playing with a particular toy? Are they being nice to the other kids? Are they playing well together? Do they play with one toy and move on to the next one quickly? That's all things that would be collected observational. The other type of data collection is experiment. And oftentimes we think of in a chemistry lab for this. So some sort of treatment is applied to part of a population called the treatment group, and the responses are observed. So this is any time you are splitting your sample into 2 groups. One group gets the treatment, one group doesn't. Another part of the population may be used as a control group, which is where no treatment is applied. The subjects in both groups are called experimental units. In many cases, subjects in the control group are given a placebo, which is a harmless fake treatment that is made to look like the real treatment. So that would be like a drug trial. If we were testing blood pressure meds, one group gets the blood pressure med and one group would get like a placebo, which means it looks the same, it's the same color, pill size, everything, but there's nothing in it. Nothing that would affect your blood pressure. And then we would measure before and after with all of our subjects to see if a difference occurred. That would be an experiment. An experiment, this is an example. An experiment was performed in which overweight subjects were given the artificial sweetener sucralose to drink while a control group drank water. After performing a glucose test, researchers concluded that sucralose affects the glycemic and insulin responses in overweight people who do not normally consume artificial sweeteners. So that would have two groups there, a group that got it, the sucralose, and then the group that got the water. Two different groups. Oftentimes with an experiment, that's kind of your clue, is look to see if they divided the groups, like divided them into groups. So here's an example. Determine whether each study is an observational study or an experiment. Researchers study the effect of vitamin D3 supplementation among patients with antibody deficiency or frequent respiratory tract infections. 70 patients receive 4,000 IU of vitamin D3 daily for a year. Another group of 70 patients receive a placebo daily for 1 year. So they're asking us if it's observational or experiment. And the thing that you want to look for is 70 patients receive something, and then another group of 70 patients receive something else. That's your experiment. Look for where it mentions having another group. That's the big clue. Number 2, researchers conduct a study to determine how confident Americans are in the economy. Researchers call 3,040 U.S. adults and ask them to rate current U.S. economic conditions and whether the economy is getting better or worse. Notice it doesn't mention anything about groups. We didn't split the groups. We're just asking them all a question. So the study, the fact that we are surveying them, in this case, it's mentioning just we're studying them and we are going to call and ask them to rate something. It's just a quick survey. I'm going to put it off to the side. Sometimes it'll actually say survey in the problem. This one didn't, but that's what we're doing. We're just calling, asking them a couple opinion questions. That is observational. We're just observing their opinions. So when it comes to collecting the data, we could also have a simulation. Uses a mathematical or physical model to reproduce the conditions of a situation or a process. Often involves the use of computers. It allows you to study situations that are impractical or even dangerous to create in real life. It oftentimes saves a lot of money and time. So an example would be automobile manufacturers use simulations with dummies to study the effects of crashes on humans. As you can imagine, we don't actually want to crash many cars over and over to see what happens. So they'll use computer models to get through a lot of the preliminary stuff until they really need the actual physical model of the car to see what happens. Other simulations would be for things like nurses in a lab to practice different scenarios, practice CPR before they're doing it on a real human, or pilots practice flying a plane before they actually are in the plane. So the next one's survey, an investigation of one or more characteristics of a population. Surveys are carried out on people by asking them questions, commonly done by interview, internet, phone, or mail. In designing a survey, it's important to word the questions so that they don't lead to biased results, which are not representative of a population. So you might think that you haven't done a survey recently, but we do them all the time in my house on receipts. After we go somewhere like McDonald's, there's a survey at the bottom. Tell them about your experience and you get a free quarter pounder next time. We are guilty of doing that one a lot. Surveys are quick. They don't have to be something super lengthy. It could be any kind of feedback that you are giving. The big thing is you making sure that you're not leading them to answer one way or another. So an example would be, something where they would ask you what negative trait they have. So why was this a bad experience? They're leading you to say something was wrong with it, as opposed to just, how was your experience? So you don't want to lead to biased results. You want to have very general, very neutral kind of statements and questions. So that way you can get the best feedback. Here's another one example. A survey is conducted on a sample of female physicians to determine whether the primary reason for their current career choice is financial stability. In designing the survey, it would be acceptable to make a list of reasons and ask each individual in the sample to select her first choice. So surveys can be multiple choice. They could also be open-ended questions. So with an experimental design, you really need three things. You need control, you need randomization, and you need replication. These are three of the things that you're checking for at the end of a statistical study as well, to make sure, did I do it well? Did I have the control? Did I have the randomization? Did we do the replication? So one of the terms that you've got to keep in mind is confounding variables. It occurs when an experimenter cannot tell the difference between the effects of different factors on a variable. An example here. A coffee shop owner remodels her shop at the same time a nearby mall has its grand opening. If business at the coffee shop increases, it cannot be determined whether it's because of the remodeling or because of the new mall. So confounding variables throw things off so that you can't tell, well, did the thing actually cause the result you wanted? Or was it something else? Or a combination of the two? The placebo effect occurs when a subject reacts favorably to a placebo, when in fact the subject has been given a fake treatment. To help control or minimize the placebo effect, a technique called blinding can be used. Blinding is the technique where the subject doesn't know whether they're receiving the treatment or the placebo. This is almost always in effect. We never want to hand out, particularly in a drug trial, hand out a pill and say, well, this is the fake one. Enjoy. We always want them to think they're getting the thing so we can see if there's actually a result or not. So blinding is almost always done. Double blind is done if we can afford it and there's time and the resources for it. Double blind makes it even better. That's when the subject nor the experimenter knows if the subject is receiving the treatment or the placebo. So experimenter here means the person who's handing it off. So the person who's in contact with the subject. That person doesn't know. The subject doesn't know. So what happens is you need a third person, somebody else that's going to be involved in this, who's going to be the organized, keeps track of the barcodes on the pills or the bottles to make sure that everything's going where it needs to go, but nobody knows what's what. So that third person is involved for a double blind. Randomization. Randomly assigning subjects to different treatment groups. If you have a completely randomized design, subjects are assigned to different treatment groups through random selection. And random selection, quick note here, that could be drawing names out of a hat. Just that everyone has an equal chance of being equally selected. Randomized block design. Divide the subjects within similar characteristics into blocks. Then within each block, randomly assign subjects to a treatment group. So your blocks could be any characteristic. You could have split people based on blue eyes and green eyes and brown eyes. Then from each one of those groups, given them the placebo or the treatment. And then in the blue eyes, placebo or treatment. The green eyes, placebo or treatment. That way, at the end of it, you could see if there was a reaction between the placebo and treatment. But additionally, you can find out whether it affected people with different eye colors differently, or maybe it's hair color or gender or socioeconomic status. Blocks could be divided any way you want. So here's an image and an example so you can see it. says an experimenter testing the effects of a new weight loss drink may first divide the subjects into your age categories. So here they are, different ages. Then within each age group, randomly assign subjects to either treatment or control. So control and treatment for each group. That way at the end, we could see if there was a difference and maybe it affects certain age groups differently. If you think of any kind of drug commercials, sometimes you'll hear things like not effective for individuals over the age of 50 or not effective for children under the age of 18. This is where they get things like that. Sometimes drugs work for certain age groups and not others. So a randomized block design would help them figure that out. Matched pairs design. Subjects are paired up according to similarity. One subject in the pair is randomly selected to receive one treatment, while the other subject receives a different treatment. This is an ideal one for cancer treatments. If they can find two individuals, so two different patients who are very similar, so a lot of the same characteristics medically, so maybe same blood type, same levels of chemo and radiation at that point, whatever the case may be, as similar as they can possibly give, and then perhaps one of them gets treatment A and one of them could get treatment B. So maybe one's getting 100 milligrams and one's getting 50. And seeing if it makes the difference. But the big thing with this is that there are pairs of people. So somebody has been paired up and they are getting something different from each other. Sample size. The number of subjects in the study is very important to an experimental design. And we'll talk more about variables, but sample size is the letter N. It is the lowercase letter n. Replication, the repetition of an experiment using a large group of subjects. Oftentimes you do it on a small scale, make sure you work out all the kinks, and then you do it on a bigger scale. So example, to test the vaccine against a strain of influenza, 10,000 people are given the vaccine and another 10,000 people are given the placebo. Because of the sample size, the effectiveness of the vaccine would most likely be observed. 10,000 in each group is a great number. If you only did it on 100, it might not be as effective as you think it is. So the larger group of people you can use, the better. So an example of experimental design. It says a company wants to test the effectiveness of a new gum developed to help people quit smoking. Identify a potential problem with the given experimental design and suggest a way to improve it. The company identifies 10 adults who are heavy smokers. 5 of the subjects are given the new gum and the other 5 subjects are given a placebo. After 2 months, the subjects are evaluated and it's found that the 5 subjects using the new gum have quit smoking. So we're looking for a potential problem here. One of the problems is we're only talking about 10 people. Ideally, we could do it with more. Replication on a bigger scale. It also doesn't tell us how we are dividing up our subjects. One of the things we'd like to do is see a split between them, that they're randomly assigned to one of the two groups. But the big one on this one is the 10. We could have more people. 10 people just doesn't seem like enough to make a conclusion like the new gum helps you quit smoking. Here's another example. Number 2, the company identifies 1,000 adults who are heavy smokers. So now we've got more people. That's good. The subjects are divided into blocks according to gender. After 2 months, the female group has a significant number of subjects who have quit smoking. So this one's like on the right track. We've got a lot of people. We split it up according to gender. That's totally fine. But then we're missing something. It never tells us, once we've split it into gender, whether the gender got one of each. So did the females get the new gum and the placebo? And then did the male group get the new gum and placebo? Because at the end it says after 2 months, the female group has a significant number of subjects who have quit smoking. So are we just talking the females all together? New gum, placebo? It doesn't really give us much information there. So it's like we're missing part of that randomized block design. It's not like fully thought through there. And make sure you don't make assumptions. Read it word for word. Sometimes they're missing little pieces, but they've started off strong. So sampling techniques. One is a census. It's a count or measure of an entire population. A sampling is a count or measure of part of the population and is more commonly used in statistical studies. So that's just coming from having a sample. Even with the best methods of sampling, a sampling error may occur. A sampling error is the difference between the results of the sample and those of the population. So maybe we just didn't have the best representative group. So we want to be able to take a random sample. So every member of the population has an equal chance of being selected. A simple random sample is where every possible sample of the same size has the same chance of being selected. So again, a simple one for this could be drawing names from a hat. Every name comes up once in the hat, you mix them up and pull it out. That's a random sample. Random numbers can be generated by a random number table, a software program, or a calculator. So you're going to have a couple problems that mention using a random number table. Right here, random number table. I will link it in our Canvas, and it will be linked on the problem that you would use it on. But it is a table out of the back of our textbook that has random numbers already listed on it. So we use it so that way when we're doing problems like this, we can have the same results. But technically, calculators and computers can also do the same thing nowadays. So we would assign a number to each member of the population. So if we wanted to pick 4 people out of 100, everyone would get a number, 1 to 100. Members of the population that correspond to these numbers would become members of our sample. So here's a situation that we could use to see in action. There's 731 students currently enrolled in statistics at your school. You wish to form a sample of 8 students to answer some survey questions. Select the students who will belong to the simple random sample. So we want to pick 8 out of 731. So we first have to assign all of those students a number. So from 1 to 731. But because we're reading this off a table, you always look at your bigger number, your total here, so 731. There's 3 digits there. So this first person also needs to have 3 digits. It's kind of like your social security number. Everybody has the same number of numbers. We all have 9. Same with your VID. We all have the same number of your VID number. So this one needs to be 001 to 731. Those are the numbers that each student has been assigned. I want to pick 8 of them. So if we look at the table, we have to have a starting point. So this case, they specifically tell us the 3rd row and the 2nd column. They will have to tell you somewhere in the problem where to begin. Otherwise, we'd all get different numbers. So here's a little blurb copied right off of your random number table. So it said 3rd row. So 1, 2, 3. These are rows over here. And then it said 2nd column. So column, column, column. These are your columns. So 3rd row, 2nd column means start right here with that number 7. And we're going to pull off the numbers in order. So it says read the numbers in groups of 3. So we have 719. And then I'm going to put a comma there. And then the next one's going to be 662. So 719's right there. Put a comma. And then 662. The spacing is just so you don't lose track of where you are. They're in groups of 5 all the way across, but that doesn't mean anything. You just skip the space as if it wasn't there and keep on reading numbers. So 662, and then we've got 738, 650, 004, 053, 589. Now you're probably wondering, when do you stop? As you keep on going, as often and as many times as you need to, until you get the numbers that you need. And in this case, they told us to pick 8. So I'm picking 8 as long as the number is between 001 and 7. Oh, I forgot the number. 734. Oop. We're going to go with 734 because I can't remember. I think that was it. So this one isn't within that range. This one's within that range. If we're going with 734, this one is not. This one is, this one is, this one is, this one is. 1, 2, 3, 4, 5, 6, 7, 8. Those would be my selected students. So I highly recommend when you're doing problems like this, write them all down and then do what I just did. Circle the ones that are in, slash out the ones that don't count, and those are your selected students. So this one, all 8 of them. Make sure you skip the one that is not in the range. It was 731. We're still good. We made it perfect. So other sampling techniques. These are some vocab terms to definitely know because we'll mix them all up and ask you multiple choice with these. Stratified sample, divide a population into groups or strata and select a random sample from each group. So divide into groups and then select a sample from each group. Stratified. So the image is you're dividing by income and then you are picking a couple from each one of those groups. Cluster, divide the population into groups or clusters, and then select all of the members in one or more groups, but not all of the clusters. So stratified is you're picking some from each, and cluster is you're picking all from some. So they're slightly different. So in this case, if we divide it based on zones, then we would pick everybody in zone 1 and nobody in these other zones. That's cluster. Systematic. Choose a starting value at random, then choose every kth member of the population. This one is just like what teachers love to use in the classroom. I'm counting off every third person is in a group. So 1, 2, 3, 1, 2, 3, 1, 2, 3. All my 1s in one corner, all my 2s in a corner, all my 3s together. That's systematic. The most important thing with that is they have to tell you what they're counting by. Is it every 5th, every 4th, every 100? It has to be stated to be systematic. Convenient sampling. Choose only members of the population that are easy to get. This is like the people in the mall with the clipboards. When you're walking by, they corner you. Hey, can I ask you a few questions real quick? It's convenient to the person that's doing the questioning. So that's convenience. Or maybe they're stopped outside of the library. They ask everybody coming in the library that day a couple questions about their use of the library. That's convenience. It's also very biased because you're only getting people who already use the library. So it often leads to biased studies. It's not recommended. it is great if you want some quick information. Maybe you're just kind of getting a feel for things before you fully do a statistical study, but it's not recommended for the long run. So here's some examples to identify sampling techniques. This one says you're doing a study to determine the opinion of students at your school regarding stem cell research. Identify the sampling technique used. You divide the student population with respect to majors and randomly select and question some students in each major. So the fact that you're picking some from all of those groups, that is stratified. Some from each group. You assign each student a number and generate random numbers. You then question each student whose number is randomly selected. That is a simple random sample. You select students who are in your biology class. That's convenient.